Hey all, and welcome to the introductory segment for your AP Biology summer work, and we're going to do a quick review of chemistry. Chemistry is going to be a part of just about every unit we do during the year, and you need to have some of the basics from this past year when you took chemistry kind of right at the top of your head so that you can recall them easily and quickly as we go through. So chemistry is just the study of matter, and matter is anything that takes up space and has mass. And as that, we're going to be looking at two main types of matter. We're going to be looking at pure elements, so substances that cannot be broken down by chemical means, so gold, iron, oxygen, hydrogen, nitrogen, and then compounds, which are two or more elements combined in a fixed ratio. So one that we'll talk a lot about is H2O, HCl, CO2, sulfuric acid is H2SO4, glucose is C6H12O6. So those are all compounds, and we'll look at them. And when we get into compounds, a lot of times there's this idea of emergent properties. So we can take two elements or two compounds and combine them and get something that has really very different properties. So in the case of salt, if we start with sodium, it's explosive in water, and if you were to put it in your mouth, you would literally breathe fire. And then we have chlorine gas, which by itself is also deadly. If you breathe it in, there's a good chance that you'll die. Yet when we combine those two, we end up with NaCl, which is vital for life. We need it in order to survive. So that's the idea of emergent properties. We have two things that have very different properties, yet when we combine them together, because of their interactions, because of the bonding that we see, it creates something, NaCl, that is very different. In terms of element, there's 92 naturally occurring elements. 25 are essential to life, and of those 25, only about 4 make up 96% of living matter. So the big 4 that we're going to concentrate on are carbon, hydrogen, oxygen, and nitrogen. And that makes up about 96% of us. The remaining 4% is a combination of potassium, sulfur, calcium, phosphorus, trace minerals or trace elements like iron, iodine, selenium, are also present. And you can see from this table right here, oxygen is by far and away by mass the biggest percentage of human body weight. Carbon is less than 19, hydrogen less than 10, and even the last of the big 4, nitrogen, is less than 4%. So you can see it very quickly falls off down to elements that we do need to survive, like magnesium, but they make up less than 0.1% of body mass. So atoms are the smallest particle of matter that retains the property of that element. When we get down to the atomic level and actually look at the subatomic particles, there's 3 that we're going to look at. In the nucleus, there's 2. There's the protons, which have a positive charge, neutrons, which are neutral, and then outside those in the electron cloud, or sometimes referred to as the shells, there's the electrons, which are negatively charged. Now with those, there's 2 ideas that we really need to be familiar with and comfortable with. The first is the atomic number, and that's just the number of protons in an atom, and that defines the element. Whatever the atomic number is, we can look on the periodic table and we can find out that's what the element is. So if we look, say it's got an atomic number of 6, we know that's carbon. But if we change it to 7, it's no longer carbon, it's now nitrogen. So the atomic number is very important in terms of defining what the element is. Now, neutrons can vary. So we can have isotopes of an element that have different number of neutrons where the proton number is the same. So the atomic mass looks at the combination of protons and neutrons. Electrons play no role in the mass of an atom, and 1 electron is less than 1/1800th of the mass of a proton or neutron. So that's why they really don't enter into the equation at all. So if we're trying to find the number of neutrons, it's going to be found by taking the atomic mass minus the atomic number. So in the case of scandium, we can look on the periodic table, we can find out that its atomic mass is 45. The atomic number is 21. So 45 minus 21 gives us 24, so that's the number of neutrons. So just by looking at the periodic table, you've got to be able to tell how many protons, electrons, and neutrons are in an atom. So here's a quick diagram on the right, shows kind of the Bohr model, where we've got the red positive particles, the protons in the nucleus, the black neutrons, and surrounding that in a shell are the negatively charged electrons. On the left is a little closer to reality, where again we've got the positively charged protons, the black neutrons, and the electrons are shown in a cloud or a probability cloud around the nucleus. And so the last thing we'll talk about in this segment is kind of the symbol that we can use. So AZX, where X is going to be the chemical symbol. In this case, C for carbon, could be Na for sodium, Fe for iron. A is the atomic mass, Z is the atomic number. And so if we go and we look at these two isotopes of carbon, we've got carbon 12 and we've got carbon 14. In the case of carbon 12, the atomic number is 6, so we have 6 protons. There are also 6 electrons because it's electrically neutral. And in this case, 12 minus 6 gives us 6 neutrons. But the lesser common isotope, carbon 14, still has 6 protons, 6 electrons, but now 14 minus 6, it has 6 neutrons, and that's how we find the neutrons, and that's how we know that these are isotopes of each other. So until next time, enjoy your summer, and we will talk to you soon.